Calorimetry going to be the topic of this lesson, and calorimetry is the study of the heats of reactions or enthalpies of reactions, and we'll find out a couple different ways we can measure the enthalpies of reactions. We'll start off with talking about a calorimeter, a lovely insulated device that is specifically designed for this purpose, and then we'll talk about specific heats as well and the lovely Q equals mCΔT equation that goes with it. Let's get into this. So calorimetry here, and notice the similarity to the word calorie. And here we're going to be measuring, the amount of heat or enthalpy produced by a given reaction or consumed by a given reaction. And we often use what's called a calorimeter for this purpose. And so a calorimeter is usually a much larger probably than what we're seeing here, but it's a very heavily insulated container, often has water in the walls and stuff like this, but it's a huge heavily insulated container. This way we can minimize the exchange of heat with the surroundings. We want whatever we stick inside here. And we're going to stick some sample in here. And we're going to do some chemical reaction with this sample and then measure the heat change of the calorimeter itself. Now, this is actually what we use to actually measure the caloric value of the food that you eat. So notice if you've got a Snickers bar that's a couple hundred calories, and this is nutritional calories, what they will do is they'll take that Snickers bar and they will stick it in one of these calorimeters, and then they will light it on fire and let it burn completely. And then they'll figure out how much the temperature of this calorimeter went up. And based on how much the temperature went up and its known heat capacity, which is what C stands for here, they will calculate how much heat was given off in the process. And then they will publish that value on your lovely nutritional label. So why do they light it on fire here and then say that that's the same thing as when you eat it? Well, again, don't forget that enthalpy change is a state function. It only depends on the initial state and the final state of the system. It doesn't matter what path you take. And if you notice, when you eat a Snickers bar is chock full of hydrocarbons, and essentially you're combining it with the oxygen that you're breathing in, O2, and then it's being converted into CO2 and water largely. So you're reacting it with oxygen and producing CO2 and water. And if you recall, that's what a combustion reaction ultimately is. Now, in your body, you're doing this over many enzymatically catalyzed steps and stuff, but the net result is the same. And if the initial state and the final state is the same, then the delta H for the process is the same as well, because enthalpy change is a state function. So that's why they're allowed to just put it inside one of these calorimeters and burn it. And figure out the nutritional calories involved with that lovely food. All right, so this is the lovely equation we're going to be using for a calorimeter. You've got to know what's called the heat capacity, which essentially is just how much heat it takes to change the temperature of this lovely calorimeter. And if you multiply it by the change in temperature, you can calculate Q. And so there's three variables in this equation. You're provided with two, you can calculate the third. And typically, you figure out what the heat capacity is with a controlled experiment, and you calibrate it in that way, and then you have that heat capacity, and you use that for several experiments, and you might calibrate it again at a future date just to make sure it's still on and stuff like this. But once you know that heat capacity, you can then do any reaction or process inside that calorimeter, and just by simply measuring the temperature change, you can figure out how much heat was either given off or consumed by that reaction. So let's look at a couple examples here. So first question: if 3,000 joules of heat causes a temperature increase of 3 degrees Celsius for a calorimeter, what is its heat capacity? So now we're being asked to solve for this heat capacity, and we're going to do something in here that gives off 3,000 joules, and we're told that the temperature goes up by 3 degrees Celsius. And the question is, what is that heat capacity? And again, the heat capacity is really the amount of joules it takes to raise the temperature of the calorimeter 1 degree. Well, if 3,000 joules raised it 3 degrees, we can maybe intuitively see that, well, then it would take 1,000 joules to raise it 1 degree, and that's essentially what this is going to be. So let's rearrange this here and solve for that heat capacity. And in this case, you can see it's going to equal Q over delta T. And so in this case, we'll take that 3,000 joules divided by the 3 degrees Celsius, and we'll get 1,000. And technically, we only need 2 sig figs. This is supposed to be 3.0. So I'll put a cap on that. But sig fig's not my main point of interest here. So, but 1,000 joules per degree Celsius would be the heat capacity on this calorimeter. And that way now I could, do any kind of reaction in the future, and based on the delta T, I could calculate Q pretty easily because it's 1,000 joules per degree Celsius. So if some, time later in the future, I did a lovely combustion reaction in here and the temperature of the calorimeter went up 5 degrees Celsius, well, if it's 1,000 joules per degree Celsius, well, then 5 degrees would mean it had a heat that was released was 5,000 joules, so on and so forth. And I wanted to use nice big round numbers for this first example because we're going to make this a whole lot harder in this next example. So question says, if 8 grams of methane, CH4, is combusted in a calorimeter with a heat capacity of 29.7 kilojoules per degree Celsius, and its temperature rises from 25 degrees Celsius to 40 degrees Celsius, what is the enthalpy of combustion of methane in kilojoules per mole? So what we're going to do here is we're going to stick 8 grams of methane in here with enough oxygen for it to combust, and we're going to light it on fire, let it combust completely. So, and then the heat released is going to be absorbed by the calorimeter. So, and we're going to figure out by how much it goes up in temperature and the provided heat capacity, what that Q of the reaction is. So the key is, again, we have the heat capacity provided, and we can calculate that delta T because we know both the initial and final temperature. And so in this case, we're going to have Q equals, and that heat capacity again was provided as 29.7 kilojoules per degree Celsius. And the delta T here, and again, a delta T, it turns out a delta anything is always just final value minus initial value. So delta T here is final temperature minus initial temperature. And that final temperature was 40 degrees Celsius. And the initial temperature was 25 degrees Celsius. And if you quickly saw that 40 minus 25 was a 15 degrees Celsius increase, great, you could have just plugged the 15 right in here. And we'll see the units of degrees Celsius here are going to change. But if we take 29.7 times 15 here, and I'll pull out a handy dandy calculator to do this, 29.7 times 15, I get 445.5 kilojoules. Now we're not done yet, because if you recall, the answer was supposed to be in kilojoules per mole. So if you take a look here, we put 8 grams of methane in there. What do you suppose would have happened had we put only 4 grams of methane? Well, if you put in half as much methane, it only gives off half as much heat, and you would have expected half this number for your value of Q. What if you would have put in 10 times as much methane? Well, if you put in 10 times as much methane and burn it all, you'd expect to get 10 times as much heat and stuff like this. So the key is we want to scale it per mole of methane. And to get units of kilojoules per mole, we need to take the total kilojoules divided by the total number of moles of methane we used. So in our case, we used 8 grams of methane. And so we need to, in this case, divide by the molar mass to convert that into moles. And so molar mass comes right off the periodic table, and 1 mole of CH4. If you look on the periodic table, carbon is 12. Each of the hydrogens is 1 each for an additional 4. So it's roughly 16 grams per mole. And so we can see that we've got exactly 0.5 moles of methane. So I made the numbers nice here to make this work easy. And so what we're going to do now is to get our delta H here in the proper units, we're going to take that Q that we just got and divide it by the number of moles, N here representing the number of moles. And so we're going to get 445.5 kilojoules divided by 0.5 moles, which is effectively the same thing as doubling this value when you divide by 0.5. So divided by 0.5 equals 891 kilojoules per mole of methane. Now we have one last little issue here. And the last little issue here, so notice I put Q reaction here, but this right here actually is the Q of the calorimeter. It's the amount of heat absorbed by the calorimeter, but where did the calorimeter get the heat? Well, it absorbed the heat because the reaction was giving off the heat. When a reaction gives off heat, that's indicative of an exothermic reaction, which would make delta H negative, but we just calculated it out positive. Well, the big deal is this. We've got system and surroundings here. We've got Q of the reaction, that's our system, and then we've got Q of the surroundings. Well, the surroundings in this case are essentially the calorimeter. We've tried to isolate it from all the rest of the surroundings. And so this has to add up to 0. The heat being given off by the reaction. So, and added to the heat being absorbed by the calorimeter, well, it's the same heat, and so that's why they're going to add up to zero. Q reaction here was negative, Q of the calorimeter is positive, and so they're going to add up to zero since they're the same magnitude. And so in this case, when we have the Q calorimeter right here, notice that Q reaction is going to equal the negative of the Q calorimeter. So when we got the Q calorimeter of 445.5 kilojoules, well, when we go to plug it in right here, so for the Q of the reaction, we should be plugging in negative 445.5 kilojoules, and that's why we're going to come out with negative 891 kilojoules per mole. And so when you're doing this, when you calculate the Q of a calorimeter, just know that your Q of the reaction is the exact opposite value, or exact opposite sign, if you will. And so if your calorimeter is going up in temperature, it's gaining heat, it's because your reaction was giving off heat and is exothermic. If your calorimeter goes down in temperature, therefore it was releasing heat, well, it's because the reaction inside was absorbing heat and was an endothermic reaction. So just keep that in mind. So, but there's our answer there. So it's negative 891 kilojoules per mole of methane combusted. So now we've got to talk about the specific heat of a substance, and we've been introduced to this just a little bit by the definition of a calorie. And again, a calorie was simply defined as the specific heat of liquid water. So it takes 1 calorie to raise the temperature of 1 gram of liquid water 1 degree Celsius. And that's what a specific heat is. It's the amount of heat it takes to raise 1 gram of a substance 1 degree Celsius. All right, so we get this lovely equation then. So the amount of heat being given off is equal to the mass of the substance you have. So times the specific heat of that substance, and then times the delta T here. And notice the similarity with our heat capacity. And the key is that your specific heat is kind of like the heat capacity per gram of the substance you have. And so then you have to multiply by the mass of the substance you actually have to get the total heat capacity of that quantity of that substance, kind of a thing. And so this times this really gets you the entire heat capacity of the amount of substance that you have, so to speak, and makes this equation look very similar to the one we had for a calorimeter. Now, big difference here. So with a calorimeter, you just have a calorimeter. How big it is, how small it is, what it's made of is irrelevant. But with a specific heat, you have a specific substance, liquid water, aluminum, copper. So you have a specific substance, you have a specific amount, and when you add heat to it, its temperature is going to go up. Or if you remove heat from it, its temperature is going to go down. And that's the relationship we're looking at here. But that's also how you recognize what you're doing. Do you actually have a calorimeter and you have no idea what it's made of? Then you're not doing specific heat. You're doing what we just did with calorimeters. But if you've got a certain amount of a specific substance, then you're looking at the specific heat equation here. And a lot of people think this looks like MCAT. mCΔT looks like mCAT, MCAT. So for those of you that are pre-health and stuff, but Q equals mCΔT is our lovely equation we're going to use here with specific heat. And we've now got 4 variables instead of 3. And so I've got to give you 3 out of the 4, and then I can expect you to calculate the 4th is the way it goes. Now, I just want to give you a little idea of what that specific heat means. Now, it turns out you've got to be specific about your specific heat as far as the phase goes, because it turns out like the solid phase, the liquid phase, the gaseous phase are all going to have different values of the specific heat. So it turns out, again, the specific heat is how much heat must be added to a substance to raise 1 gram of that substance 1 degree Celsius. So it turns out for liquid water, it's 4.18 joules per gram per degree Celsius. So if you have 1 gram of water, it's going to take the addition of 4.18 joules of heat to raise the temperature up 1 degree. Well, what if you wanted to raise it up 2 degrees? Well, then it'd take twice as much heat. What if you wanted to raise up the temperature of 1 gram of liquid water 5 degrees? Well, then it's going to take 5 times as much heat. And that's why we multiply by delta T. So going back again, it takes 4.18 joules of heat to raise the temperature of 1 gram of liquid water 1 degree Celsius. Well, what if you had 2 grams of water and you wanted to raise it up 1 degree? Well, if you had twice as much water, then it would require twice as much heat. And what if you had 5 times, as much water? So 5 grams of water. Well, then it would take 5 times as much heat. And that's why we also multiply by the mass in this equation. And so again, the specific heat is for 1 gram, 1 degree Celsius. So if you have more or less than 1 degree Celsius, you have to multiply by that delta T, that temperature change. So, and if you have more or less than 1 gram, you've got to multiply by how many grams you have as well. And that's kind of the origination of that lovely equation. But like I said, It's got 4 variables. I give you 3. You solve for the 4th. Let's take a look at, oh, actually, got to one last thing about the conceptual difference here. So notice liquid water's got a specific heat of 4.18 joules per gram per degree Celsius, whereas solid aluminum, 0.9 joules per gram per degree Celsius. And you should realize what this means. So when you look at these, you should realize that this is the explanation for why, if you had a kiddie pool full of water sitting next to a park bench in Arizona in August, and they sat out the same amount of time out in the Arizona sun in the heat of the day, which one would you much rather not touch if it's the same mass in both cases? So same mass of water, same mass of aluminum. Well, you don't want to touch the aluminum park bench because it's going to be hotter. And the idea is with a lower specific heat, it takes less heat to raise its temperature each degree. And so the sun's hitting the water and the sun's hitting the aluminum park bench, and giving them the same amount of heat. But giving them the same amount of heat, the temperature is going to change to a much larger extent with the aluminum with that lower specific heat. So again, looking back here, assuming they had the same mass and they're getting the same heat from the sun, so then the one with the lower specific heat is going to have the larger delta T and end up at a hotter temperature, and it's going to be hotter to your skin and more likely to burn you. Cool, so that's how that works. So conceptually, you should think of, giving the same amount of heat to two substances, whichever one has the smaller specific heat is going to end up with the higher temperature, the larger temperature change. And again, at first that might seem a little counterintuitive, but that's kind of the level you want to understand it with. Let's take a look at some calculations here. So now we're going to take a look at doing some of those calculations. We want to first explore what's called a heating curve. So and it shows kind of what happens temperature-wise when you add heat to a substance. And in general, we think, oh, yep, we add heat to a substance, its temperature is going to go up. And usually that's true, except during phase changes, as we'll see here. And so it turns out that when you add heat to a substance and its temperature stays constant, that's indicative of what happens in a phase change. And so if we take a look at this heating curve for water, for instance, so you add heat way down here to a substance and it's going to go up in temperature. And that's when you've got solid water not going through a phase change. And if you want to calculate the amount of heat associated with that temperature increase as it goes up in temperature here, that's where we use mCΔT. So, but once you hit that freezing or melting point of water in this case, so which you and I both know is going to occur at 0 degrees Celsius, the melting temperature for water. Once you do that, it turns out just to melt the ice, it takes extra heat. And so as the extra heat required just for the melting process happens, there's no temperature change, just the water is being converted from the solid phase to the liquid phase. But once it's all in liquid phase, that temperature is going to start to go up again as that liquid water begins to heat up as well. And again, as long as you're not going through a phase change, that's what mCΔT allows us to calculate the heat involved in the process. All right, so but once we hit the boiling temperature here, which we know for water is 100 degrees Celsius. So once again, it takes extra heat just to turn the water from liquid phase to gas phase. And so the temperature is not going to increase even though we're adding more heat, but the temperature doesn't go up at all. But once it's all converted into the gas phase, then once again, the temperature will start to go up and you can once again use mCΔT to calculate how much heat's involved there. So our lovely Q equals mCΔT is not everything we need here. It allows us to calculate heat changes as long as we don't pass through one of the phase change temperatures. So if we stay in the solid phase or we stay only in liquid phase or if we stay only in the gaseous phase, we're good. But if we do pass through one of these phase changes, we'll notice there's no temperature change. There's no delta T. And so this equation can't help us. And so what's going to help us is, turns out we're going to look up some thermodynamic values, some thermodynamic quantities. And in this case, we might look up the delta H of fusion. And in this case, we might look up the delta H of vaporization. And so in this case, to calculate the amount of heat or enthalpy associated with this, we're going to take that delta H of fusion, which is usually provided in kilojoules per mole. So it's a scaled value for 1 mole, so kilojoules per 1 mole, and then you'll multiply by how many moles, N here, of the substance you have. So if you have 2 moles, you'd take 2 times that delta H of fusion. So same thing with the delta H of vaporization up here as well. Now, one thing to note, I said that the delta H of fusion, melting, and the delta H of vaporization, boiling, are usually provided in units of kilojoules per mole, and that's why you got to multiply by the number of moles of that substance that you actually have. However, they also can be reported in units of kilojoules per gram instead. And if that's the case, well, then instead of multiplying by the number of moles N, you'd end up multiplying by the number of grams, M, the mass, instead. So just a FYI. So here I'm representing it in the most common form you're likely to see it in, but just know instead of kilojoules per mole, the delta H of fusion vaporization could be provided in kilojoules per gram. So be careful there. So but this is your heating curve, and we're going to use it to solve the next problem here. And basically, every time you hit one of these corners, you have another step in the calculation that you're going to perform. So let's take a look at the next question here. And next question says, how much heat would be required to raise 90 grams of ice at negative 20 degrees Celsius to 50 degrees Celsius? So we're being told that we have 90 grams of ice and that we're somewhere down here at negative 20 degrees Celsius. But then we're going to end up at positive 50 degrees Celsius. So we're going to end up somewhere right around here, which would mean we're going to end up right here. And so we're going to have a few steps in this calculation. We're going to have to heat up the solid to that corner right there. We're then going to have to melt the solid to that corner right there. And then we're going to have to heat up the liquid up to that point right there. And so there's going to be three parts to this calculation: step 1, step 2, and step 3. And step 1 and 3 here that I've highlighted are going to be mCΔT calculations, but step 2 is going to involve the delta H of fusion. So on the study guide here, I've provided all the relevant thermodynamic data for water. And again, if you look at that, and I'll put it up on the screen here somewhere, the solid, liquid, and gaseous phases for water all have different values for the specific heat. So you got to make sure that, like, if you're doing this part of the calculation right here, that you're using the specific heat value for specifically the solid phase. And if you're doing the mCΔT calculation right here in step 3, that you're using the specific heat value for liquid water instead. Cool. And then also I've provided the delta H of fusion and vaporization. Obviously in this particular problem, we only need the delta H of fusion, not the delta H of vaporization. But one of the things professors often know is that if you give students more data than they actually need, they're more likely not to get the question right. So here I've given you any possible data you could have needed, and we're not going to use it all. So, but let's take a look at how this works, and I'll break this up into steps 1, 2, and 3. And again, step 1 is going to be mCΔT for the solid phase, whereas step 3 is going to be Q equals mCΔT for the liquid phase, and then step 2 is going to be N times the delta H of fusion, and again it's N in this case because the delta H of fusion I provided was in units of kilojoules per mole. All right, so in this case we've got 90 grams, that's our mass, times the specific heat again of solid, and that's given as 2.09 joules per gram degree Celsius. And then times the delta T. And in this case, we're going from negative 20 up to 0 degrees Celsius. And again, final minus initial, 0 minus a negative 20. So it's 20 degrees. And this is going to be important. The sign is really important here. And so in this case, when you're going up in temperature, when you do final minus initial, it's always going to end up positive. Whereas had we been going down in temperature, then final minus initial would have ended up negative. And the sign is really important. So as long as you do the correct final and the correct initial, the sign should work its way out. So, but in this case, if we do 0 minus a negative 20, we're going to get positive 20 degrees Celsius for that part of the calculation. And at this stage, I like to do set up parts 1 and 3 since they're both using mCΔT at the same time, just to save some time. And so again, 90 grams. And in this case, we want to use the specific heat. And I provided you with CS. Some other books will use lowercase c, but I'll go with the capital CS here to be consistent here. My bad. And then we've got to use the specific heat of liquid water, now provided as 4.18 joules per gram degree Celsius. And again, times delta T. And for the liquid phase in step 3, it's all melted at 0 degrees Celsius and then raised in temperature up to 50 degrees Celsius. So final minus initial, 50 minus 0 is 50 degrees Celsius. And there's our setup. And we'll use our calculator to get some numbers here. And then for the phase change here, we first got to figure out how many moles we have because the delta H of fusion is provided. So in this case, it's given as 6.01 kilojoules per mole. So we don't want to multiply by 90 grams. We want to multiply by how many moles we have. So we're going to take that 90 grams of water. We'll just do this down at the bottom here. And we'll use the molar mass to convert it to moles. So we need grams of water in the denominator to cancel, moles of water on top, and molar mass is always for 1 mole. And again, oxygen is 16 off the periodic table. Atomic mass for hydrogens are 1 each, for a total of 18 grams per mole. And 90 divided by 18, it turns out I made these nice numbers, is exactly 5 moles of water. And that's what's going to get plugged in right here. All right, so now we'll let our calculator go to work here. And we'll take a look at the units real quick. Notice the grams here cancel, the degrees Celsius here cancel. You get your answer in joules. Here the moles are going to cancel, and the answer comes out in kilojoules. And once again, here the grams cancel, the degrees Celsius cancel, and it comes out in joules. So 2 of these are going to come out in joules, 1 in kilojoules. We'll have to make sure the units match before we actually add them together. Otherwise, we'll be trying to add apples and oranges. All right, so we'll take 90 times 2.09 times 20, and we'll get 3762 joules. All right, and in this case, I'm actually going to do this one. Actually, now we'll just go in order. So 5 times 6.01 is 30.05 kilojoules. You might have been able to do that in your head. And once again, 90 times 4.18 times 50 is 18,810 joules. So in this case, if this was a multiple choice question, you were trying to figure out the answer, I would look down at your answers. If they're all in joules, well then convert this one to joules before adding them. If all the answer choices are in kilojoules, well then let's convert these into kilojoules before adding them all together. So in this case, I'm going to look for the answer in kilojoules, just to my personal preference, and I think that's the most likely set of units you'd be likely to see. And so in this case, we'd convert this guy here. We just move the decimal back 3 places, divide by 1,000 to get 3.762 kilojoules. And this one here, we do the same thing, move it back 3 places, dividing by 1,000 to get 18.81 kilojoules. And now we could go and add these together. And we see that most of the heat was actually involved in the melting step, the phase change step, and that's pretty common for most substances here. So we'll take 3.762 plus 30.05 plus 18.81 and get 52.622, which I'll round to probably 2 decimals. So 52.62. Cool, and that's the total amount of heat required to take, again, 90 grams of water starting at negative 20 degrees Celsius as ice and heating it all the way up to 50 degrees Celsius as a liquid. Now, one last little thing here, and I really wish I'd done this earlier, but better late than never. And I wanted to point out a couple things on the heating curve here. And actually, now that we've looked at the values, maybe it makes more sense now anyways. So, but a couple things. Notice the delta H of fusion and the delta H of vaporization, and that the line for the delta H of vaporization is longer than the delta H of fusion. And the reason for that is that it typically takes more heat to boil a substance than it does to melt a substance. In the case of water, you're looking at 6.01 kilojoules per mole for the delta H of fusion versus 40.65 kilojoules per mole for the delta H of vaporization. So technically, it should actually be quite a bit longer, but that would get ridiculous. Or I can make this one quite a bit shorter, but it would have been too small to really notice. So that's the way that works. And the other thing is dealing with the slope of the line for the solid, the liquid, and the gas. And notice that in the case of water, the liquid has a smaller slope. So, and that smaller slope is indicative of a larger specific heat. Notice that for the solid and the gaseous phase, they're both really close to 2 joules per gram per degree Celsius. But in the case of liquid water, it's double that, 4 joules per gram per degree Celsius. And so it's going to take more heat to raise its temperature, and that's evidenced by a little bit lower slope here. Cool, and I have no idea if you can hear the rain and the thunder that is going on right outside this window. It is a little bit crazy. But that is the completion of this lesson. If you have found this lesson helpful, consider giving me a like. Best thing you can do to make sure that YouTube shares this with other students. And if you're looking for practice problems, practice final exams, final exam rapid reviews, check out my general chemistry master course at chadsprep.com. I'll leave a link in the description. A free trial is available. Happy studying.